Hey there, everybody. How are we doing? To all of those very few people out there. There you are. How's it going? We'll wait a minute for people to hop in. Pretty good? Me too. Yeah, I'm feeling pretty good. It's a nice Sunday. Hey, Neuro. How it going? Good. Very good. Interesting. How about myself? I'm not doing too bad, actually. I stayed up late last night working on this stuff, and then I went to bed at around 3 a.m. and then my body decided that was enough, so it woke up at 6. And then I took a long shower, and then started up my computer and decided, okay, I guess it's time to start the day. But then after a few minutes of just kind of sitting there, I just thought, what am I doing? Why am I being so dumb? Just go back to bed. And I did, and I then slept another 6 hours. So here we are. Oh, that's loud. Oh, that's so loud. Pause. Down. Sorry about that. Yeah, 6 a.m. bring. Yeah. Oops. That's me hitting the mute button. This is a fun song. Okay. Well, how about we get started? I'm glad you got some sleep, and you got some good old math physics. Yeah. It took me a minute. It took me a while to kind of wrestle with the problem that I was encountering, because I was trying to implement a method that I had never used before, but I thought it would be really cool to kind of figure it out and show it off on stream about what Mathematica can do. But anyways, let's get started so we can get to that. So welcome everybody. Today we're going to be talking about the double pendulum. Oh, that'll make a difference. And I will spoil it right now and say that this single pendulum section of the notebook does not have anything in it. If you can see over here on the grouping, I did not get to that It was just going to be kind of a review, but just because I think it would be nice to have in this notebook here, which I am going to publish at some point. We'll just kind of have it out there for anybody who wants to kind of see, anybody who wants it. And so that'll go in later. We can either do that on stream, maybe, or not. It should be pretty quick. It would just be a review. But we're not talking about the single pendulum today. We are talking about the double pendulum, which you can see right here in this very handy graphic. Thanks, Wikipedia. And so Neuro, sounds good. I'm going to be back later, cooking for fam. Hope everyone enjoys the stream. Thanks, Neuro. I also hope everyone enjoys the stream. But yeah, so in this stream, we're going to be talking about the double pendulum and kind of seeing how we can implement the physics, kind of starting how we can implement the physics into Mathematica and then let it do all the heavy lifting and not exactly number crunching, but rather symbol crunching. So basically, we're going to start at the beginning and then let Mathematica kind of do the symbolic manipulations for us. But yes, so today we're going to be approaching the double pendulum via Lagrangian mechanics. And so basically, for those of you who don't know, Lagrangian mechanics is an alternative way to describe the world around us, alternative to Newtonian mechanics, which looks at force vectors and things like that to describe the motion of masses. Lagrangian mechanics focuses on the energies associated with masses, and via some very clever math and physics, using just those energies, you can get exactly the behavior of the system, or rather the equations of motion that the system will follow. And so that's what we're going to do today. And so, moving down, our first step, getting the Lagrangian. So, we go over here, and we open up our little thing. And so, our first step in getting the equations of motion via Lagrangian mechanics is getting the Lagrangian, which just comes in the form, in our very classical form, we're not doing any quantum here, of the kinetic energy, the difference between the kinetic energy and the potential energy. Let's just a little less. There we go. Yeah, and so that's just kind of where we're going to start with that idea in mind. Okay, well, now we need to find the kinetic and potential energies. So let's do that. So let's see what's going on in the potential energy. So, how I like to approach things is kind of from the very beginning and go very step by step, baby steps, because I like to have a firm grasp on exactly where everything is and how everything relates to each other. Also, feel free to ask questions at any time about Mathematica or the physics or math going on. Especially this kind of paragraph coming up here. It's very wordy because I wrote this in, obviously, Mathematica and not LaTeX. So, but yeah, feel free to ask questions at any time. And, yeah. So, with the potential energy, you need to define a 0 point and positions, and using those two things, things kind of fall out pretty nicely. But if you have a good definition and a good grasp on the position of, say, your mass, then you can get the potential energy pretty easily. So that's where we're going to start. So, yeah, so considering this diagram and kind of in our heads thinking about if it's just hanging straight down, where the yeah, where both masses are just hanging straight down. And so we're going to call that the rest position. And so in that rest position, mass K, either 1 or 2, is a distance of L1 below its support, the support above it. And so, of course, that gives us that mass 1 is a length L1 below the topmost anchor point, and then mass 2 is distance L2, again, if we're hanging straight down, a height of L2 below its anchor point above it, M1. But so, and then, of course, that gives us that we just add the 2 if it's hanging straight down, that we get L1 plus L2 as the distance of mass 2 from the topmost anchor point. And so what happens then, if we, so with our kind of rest position, our rest heights in hand, we can talk about actually displacing these things, displacing the masses now. And so when we displace mass K by an angle phi K from the rest angle of 0 from the vertical, that mass K is a distance Lk times cosine of the angle it has been displaced above its rest height. And so it's moved up Lk cosine phi k. And so just looking at our diagram here, it's easy to see a little trig. And so if this is our angle, then we take, okay, this is our adjacent thing, and then it rises up by some multiple of the kind of connecting rod, rigid rod. And so it rises up that much from its rest height. But if we turn our attention specifically to the second mass, if the first mass rises, then so does the second mass, even if it doesn't do anything. So, since the height of the second mass rises with that of the first, the second height, or the height of the second mass rises by a distance of L cosine, or L1 cosine phi 1, the amount mass 1 has risen, plus the amount that mass 2 has risen, or rather L2 cosine phi 2. And so, you know, in a sentence, the amount that the second mass has risen from its rest height is L1 cosine phi 1 plus L2 cosine phi 2. And so therefore, when moved, the height of each mass relative to the anchor at the top, is then the difference between its rest height and the height above its rest height. And so now we're moving to measuring our distances of each mass from the topmost anchor point. And so what that comes out to be is, so the mass 1 anchor distance, it comes out to be, we're defining it as H1, is L1, so its rest height minus the height it has risen. And that comes out to be L1 times, and then, you know, we can rearrange that and then pull out the L1 to get kind of this expression here. L1 times 1 minus cosine of phi 1. And then similarly, we take the rest height of mass 2 and then subtract the amount it has risen when displaced by an angle phi, which is over here. And then we get this good old doodad. And so kind of already things are getting a little complicated relative to a single pendulum. Okay, so now that we have our distances kind of well defined, and which is, again, how I like to think about it, starting from the first step and getting a good grasp on it, we can now move on to thinking about our potential energies. Because if you recall, the potential energy takes the form, or the potential energy due to gravitational field takes the form just mgh. Well, we already have our H's. And so getting the potential energy is easy. You just slap an mg on there. And so, of course, those take the form. The potential energy of the first mass is just a multiple of that height. And then similarly, the potential energy of the second mass is likewise. And I'm not gonna read all of these out because you can see it right there. That's very small though. So why don't we zoom in? There we go. That's probably much better for you guys. And so yeah. And then so with those individual potential energies in hand, we can easily get the total potential energy of the system, which is just the sum of the individual potential energies. And so we just add them together, and we do a little bit of expression manipulation. And so we can collect our masses into a sum, and then kind of the height that the first mass has risen. And so now we have an interesting interplay between the masses and the height of the first mass, and then also the kind of change in potential energy of the second mass from its initial potential energy, because this is the sorry, because this is the height that it has changed, the second mass, that is. And so even within these mathematical expressions, they're not meaningless. The terms that we see can be interpreted as physical quantities themselves. The tie back to the real world isn't lost when we move around terms. But so now that we have our potential energies, our total potential energy of the system written down, we can, or now that we have it, written down and we've thought about it mathematically, we can say, okay, well, the whole point of this is to kind of show, to model it computationally, and so let's actually put it in the computer. And so, just like we did mathematically, we define our heights, h1 and h2, to be what they were. And then we can define a general function for the potential energy just to be mghk, or the potential energy of the k mass k, to be that mass, and then times the height, g times the height of that mass, and we already have those defined up here. And so that's an easy enough definition, just like we did mathematically. And so we can do those, and then, oh, I guess it helps if I run it. And so we can see that the potential energy, so here I'm using an array, and so I also have this tf command, which is, I decided, short for Taylor form. And so I kind of played around with it to kind of make expressions kind of look the same as they do in Taylor's classical mechanics, which is the reference I've been going off of. And so, if we look at our potential energy of mass 1 right here, and then our potential energy of mass 2, they should look the same as we have written them up here. So look at that. We have L1, and I'm also using len for the length of each kind of rigid rod. And yeah, and so we have L1 M1 times G, and then Mathematica sometimes likes to play with negatives in order to get its expressions into what it interprets as a simplified form. And so if we just pop this negative into this expression here, then we get cosine of phi1 of t, because the angles do change in time. Then we have 1 minus cosine. And that's exactly what we had up here. And then likewise for the second potential energy. But basically, all that being done, we now have our total potential energy of the system right there. And so we can actually just look at that. Well, we can go like that. And then I also have a notation function to kind of make things a little more human readable. So we say potential energy total of T, and then we say, okay, well, let's kind of format that a little bit. And is this still too hard to see? Also, are there any questions so far? Is it just you out there, Emergency? Hey, Tropical. Torn between two streamers. We'll be jumping back and forth. That's okay. Oh, hi, Doe. Yeah, moving symbols around, that's kind of just what we're doing right now. Yeah, it's all pretty good stuff so far. And of course, we're moving through this at a much quicker rate than how I prepped it, so we may get to as much as I have prepared relatively soon. Just here for the learns. Well, that's all I ever aim to do. Okay. But yeah, so we can also... Sorry about that. Yeah, we can also kind of tell Mathematica to kind of format this expression here, a total potential energy, into a more like mathematical representation, the font, literally. And we can gather terms to give us a little more physical intuition about it. And so, something that's much easier to look at and read than this mess of symbols. And so now we have our total potential energy of the system. And so we're half done getting to the Lagrangian. So now we can move on to the kinetic energy. So I'll come over here. So now this is where things get a little trickier. But yeah, so much like the potential energy, let's start from the beginning and take baby steps, getting a firm grasp on everything as we go along. And so, to be explicit, the tangential velocity of each mass is relative to the anchor at the top. So we're not using rotational kinetic energy or rotational velocity here. We are using the tangential. And so, kind of as you would expect, the velocity, the velocity vector of the first mass is, what am I saying here? I mean, it takes this form, and so this is kind of just the time derivative of our arc length that it travels over a distance, or over an angle feet. And then, of course, in the phi direction, the tangential direction. And so this part is where it's going to come into play. And we can see some interesting Mathematica code coming up. Or we will see. And so, teaching is hard, everybody. Also, yeah, feel free to ask any questions at any time or whatever you want. But yeah, so just straight addition of velocities. The velocity of the second mass is just the sum of the two velocities. But the difference here, or the key part here, not difference, is that these tangential angle, these tangent vectors are not the same. And so we have phi 1 hat and phi 2 hat. And so that's going to be important. But yeah, so those are our velocities of each mass, tangential velocities. And so that's kind of all you need to get the kinetic energies. And so we move on. Because, if you recall from probably Physics 101, the kinetic energy of a mass moving with velocity vector v, is 1/2 times the square of the norm of that vector. And so thus, the kinetic energy of the first mass is 1/2 mv squared, and in our case, the norm of our mass 1 velocity is just the square of the, well, only component of that velocity. Well, of the coefficient on the direction. And so that's exactly what we have here. And so, moving on to the kind of kinetic energy of the second mass, which is, remember, kind of dependent on the direction that the first mass is moving, we get a little trickier. And so, mathematically, this is relatively easy, but computationally, we can, it gets a little interesting. So, 1/2 mv squared. And so in our case, this kind of squared norm over here ends up being this whole deal. And so exactly how that comes from, we can recall that the squared norm of a vector is equal to the vector dotted with itself. And so if we expand each of these, then we get our sum of kind of tangent vectors. And then using the properties of the dot product or the inner product, it's linear, and so we kind of get we get a FOIL action, and then so we end up getting the kind of same thing in the velocity of the first mass. And so, square the components, or rather this coefficient times the dot product between phi hat 1 and phi hat 1. And since these are the same vector, and notably they're unit vectors, so that their dot product is just 1. And so that simplifies to just L1 squared phi prime squared, or phi dot. And then moving along, but so if we FOIL it out, then we get this term dotted with this term over here. And so then we get a product of coefficients, L1 phi 1 dot and L2 phi 2 dot. But then we have the dot product between our tangent vectors. And then we get the same thing for the next term, because the dot product is symmetric. And so phi 1 hat dot phi 2 hat is equal to phi 2 hat dot phi 1 hat. And then, so those are the same. And then so we get our product of coefficients. And then this is where we take into account that these tangent vectors are not necessarily in the same direction. And so how do we represent that dot product? Well, it's actually just equal to cosine of the angle, or the difference of the angles that the two pendula are at. And so, as I mentioned before, the tangent vector dotted with itself is 1, because it's unit vector, but it also, the same thing follows from this. Because if the tangent vectors are the same, the angles are the same, and so then you get a difference of equal quantities, which is just 0, and the cosine of 0 is just 1. So we can represent this dot product between not necessarily orthogonal unit vectors as cosine of the difference between the angles of those, or at which the pendula are. And then much like the first component, we get, really the same thing. And so we get L2 squared, and then phi 2 dot. squared. And so with all of that said and done, we say, oh, hey, that's exactly what we got. Okay, so Do says we're quote-unquote stacking our pendulums, right? Like in the Discord photo, a double pendulum. Yes, yeah, so exactly this. Now that we're zoomed in, you can see the rasterization on it. But yes, so this is the system we're working with. Okay. And yeah, and so then we have the norms of our velocities, or rather the square norms, and so we slap those into our kinetic energy formula, and then we get the individual kinetic energies of the two masses. And so since energy is so great, the crux of the beauty of Lagrangian mechanics is that you can just smash energies together and call it good. And so then the total kinetic energy of the system relative to the topmost anchor point, you just add the two, or you add the energies of the individual masses. And so that ends up being this whole big, beautiful deal. But so, just like with the potential energies, now that we have kind of the idea in our head and a good grasp on the physical situation, we can actually put all the math kind of starting from the beginning, starting with the velocities and the relationships between these tangent vectors. And we can say, just go up here, and then coding this part is easy, just like it is mathematically. And so we can just kind of start from the beginning and then let Mathematica do all the work. So we scroll down. 1 second. So this is where the code gets interesting. So, code time. So this symbol, well, okay. I'll kind of start big and then go in. So this statement right here is basically saying, if you were to read it in English, this piece of code right here says the phi vectors are defined such that the dot product between the k phi vector and the j phi vector are defined such that the phi vector is defined such that the dot product between two of those vectors is cosine of the angle between those vectors. And so, how to read this Mathematica code is we can go over here and we say, okay, what the heck is this symbol? This looks similar to our set delayed and how we kind of normally define a function, but it's not exactly. And so what we can do is open up our documentation and then come over here and we say, like, what exactly is this doing? That's interesting. There we go. And so this is the infix form of upset delayed. And so exactly what it is it assigns the right-hand side to be the delayed value of the left-hand side and associates that assignment with the symbols that occur. You can read the definition yourself. Probably not behind chat, though. You know what? Where is... overlay. Oh, I need to change that elsewhere. Okay, never mind. So anyways, okay. Emergency says, how can you use T on the left instead of T underscore? Right here. Yes. Okay. So I don't put T as an T with an underscore here because I'm not really interested in, what is this song? I'm not really interested in in substituting a value for T. I'm just keeping everything symbolic right now. What I'm actually interested in is kind of substituting in, or creating a relationship between arbitrary values of K and J. Does that make sense? Yeah, so anyways, so T could be anything. I mean, you could. Okay, so here's the story the Jedi won't tell you. Usually, we say to define a function in Mathematica, say with set delayed, and we use that. And we say, well, let's practice prudent programming, even for a small example. We usually say, okay, this is how you define a function using set delayed. It even has nice syntax highlighting. The x's are green, and it's all nice and good. And so now we can come down here and we can say, okay, f of 1, or f of t just gives t, and it does that. So, you know, how we interpret this, how we, in our head, is that, okay, you know, we give f some value and it outputs that value. And that's exactly what happens here. But what they usually don't tell you is that you do not need this colon. Usually. And so because, well, and we can go like that. And look at that, it still works. And so the reason behind that has to do with what's called the down values of f. And so, well, here, this is what we'll do. We will do that. And then so we will evaluate that. And then we will also clear f, and then f of x equals x. And then we can also look at the down values for f. And so clear, this function clear does also clear, well, it clears the down values is what it does. And so if we do that, then we can see that the actual down values, how Mathematica is interpreting what to do with this function f, is exactly the same. So equals evaluates the right-hand side, right? Yes. So yeah, the nut of the matter here, the crux of all of this, is when it comes down to the order of operations that Mathematica does. So basically, well, I wonder if, okay, we're going to delete that, and then we're also going to open a new notebook, and it's going to go like that, and we're going to zoom in so y'all can see. And so if we say f of x equals well, yeah, we can say the difference comes to when you are defining a function that isn't exactly literal, but rather it actually has to do some undefined, or not undefined, but some actual computation on the right side. But even then, so for instance, we can say, okay, so let's clear f, and then we're going to integrate, say, x from, well, xp, integrating with respect to xp, from 0 to x. And so then we can look at the down values of f, and we see, okay, Mathematica is saying, upon encountering f of something, replace that, or replace x into this expression, and then evaluate it. That's what this is saying. That's what this relationship between these two things tells Mathematica. But what we can also do is come down here. We can take out our colon, and then this operation on the right will evaluate immediately, and then associate that evaluated expression with f. And so we can see that by this. And so that's exactly kind of the idea behind this command, this operation being set delayed. You're delaying the assignment until you replace the value that you give f into this expression. So Doe says, Mathematica definitely has a syntax of its own. Yep, definitely. And I mean, with things like this, looking at the down values and having like understanding exactly kind of what's happening, how Mathematica thinks in kind of the back end while it's actually doing operations is, I mean, it took me quite a while, but now I just know it. So, and I can explain it like this. But yeah, and so now if we were to say up here, well, we can say in the same cell, so we kind of do everything over again, we can say f of 1, and then why don't we actually throw that in a timing function. And so, okay, so what this is saying is, okay, Mathematica sees f of 1, and so it goes to this table of down values, and it says, okay, I see f of 1. Okay, here's f of 1. Replace the argument into this expression. So, boom, integrate xp with respect to xp from 0 to 1, and then integrate it. And then we get half. And that took this many seconds. If we go down here and we say f of 1, then it says, okay, I see f. Let me go speaking as Mathematica here, but I see f. Okay, let's go to the table of down values. Okay. In this form, I see f of something. And so, okay, take that something and put it into this expression and then evaluate it. And so then we get f of 1 squared over 2 immediately without doing any integration. It gives us 1/2. And we can see that actually took on the order of microseconds instead of, what is that, 53 milliseconds? 10, 100,000. 2 milliseconds? Yeah, 53 milliseconds. So there is a difference. I would not suggest I would not suggest to people learning Mathematica for the first time to not use, what did I just say? I would suggest people learning Mathematica to stick with the delayed definition, also because it has nice syntax highlighting. And you don't get that syntax highlighting if you do not use set delayed, because over here x is green and over here x is blue. Okay, but anyways, so emergency says it also works when you want a random, right? F of nothing equals random versus f of f of nothing is directly set to random, which is actually a deprecated function, versus f of nothing is using delayed set random. That is exactly correct. And so what we can do is we can say okay, that is actually a really good example. I think I actually have that example in my notes that are available on the website, for those of you that don't know. If you go to that website, Science for the Busy, in the Mathematica tab, I have a guide and my notes on kind of the basics of Mathematica. But yeah, and so we can say, so f of nothing is, say, random integer between 0 and 1, which is really just 0 or 1. And we can also say g of nothing, and so is, well, is that. But let's not look at these. And so then we can say table f of k and then g of k. Oops. And then, I don't know, do k from, I don't know, 10 times. What happened? Oh. That's because I did not define f and g to take arguments. Right, emergency, yeah, that was a mistake. And so what we can see here, which may be more illuminating if we transpose this, is that, okay, f is, okay, first evaluation 1, 0, 0, 1, 0, 0, 1. And so there's that. But then as we can see, upon evaluation of g, it always gives the same thing, because if we go back up here and look at what it's doing, we can see g, now in this case it's 1, has immediately evaluated to this, has evaluated to 1, and then assigns that evaluated value to the call of g. And so, yeah, that is a really good example of the difference between using set equals and set delayed. It has to do with what happens at the time of call, and set and assignment. But yeah, any other questions, anyone? No questions? Okay, if there are no more questions, then I will move on. Okay, so we're just going to keep this notebook hidden away for a moment, or while we go along. Okay, so where was I? Let's actually minimize you too, and then we'll go back over here. Okay, so I believe we were talking about kind of this relationship, telling Mathematica the relationship between the different phi vectors, the different tangent vectors. And so now that we've told it that, we can kind of go on to actually defining our velocities with the intent of easily defining our kinetic energies. And so we can just easily say the velocity associated with the k mass is kind of lk, and then the velocity, or what am I doing? It's exactly, that's not the velocity, is exactly this. L1 phi prime, and then in the phi direction, phi vec. I probably should call this phi tangent. But anyways, and so doing that, now we have an arbitrary definition, or a function definition, and then we can kind of stipulate that that the velocity of the second mass is just the sum of the, well, kind of given this definition for our velocities, is the sum of the velocity of the first mass and the sum of the the sum of the first velocity and the sum of the second velocity, but then by themselves type of thing. GZB, welcome on in. We are looking at the physics and computational implementation of the double pendulum. And so right now we are looking at the computational implementation of the velocities associated, well, the velocities of the two masses, with the intent of the next step being to get the kinetic energies. So we can put that into the Lagrangian or with the potential energies, and then we can just keep going from there. But welcome on in. Okay, so now we have, and if we go over here, if we tell Mathematica to show us this, yeah, this is where we're at. Oh cool, the derivations would be so interesting. Yep, and so I've also included the mathematical derivations in this notebook as well. And I'm going to make this notebook available on my GitHub whenever I get it actually set up. And so it'll be freely available and easily accessible to anybody who wants it. And so if you have your own copy of Mathematica or access to one, then you can play around with it yourself, as well as having the mathematical derivations included. Okay, and so moving on, or not moving on yet. And so kind of with this piece of code here, we can see that it comes out to be exactly what we want. This velocity of the second mass relative to the anchor at the top is the sum of the velocities of the individual masses relative to the support above it. But we don't actually need to look at that. So let's get rid of it. Okay, so now that we have our velocities in hand, and we have a good grasp on exactly kind of what's going on, we can just throw those into the simple, more or less, kinetic energy expressions or definitions. Okay, so GZB, but is this implementation for 3D or 2D? This is just the 2D double pendulum. I could do 3D. So Emergency says, if you can't upload to the cloud, by the way, you can copy and paste an entire notebook to the cloud. Right. Yeah, so you're saying like with Mathematica online type of thing? Yeah. Yeah, I could do that. Yeah, I'll look into a few different ways to maybe get the things out there. But yeah, so now that we have our velocities in hand and the relationships between the tangent vectors, we can move on to our kinetic energies. And so, just using the standard kinetic energy formula for a linear velocity, 1/2 mv, or the square norm of the velocity vector, which is equivalent to dotting it with itself. And so again, this kind of formulation is what's called a pure function. And so we could say, create a whole other function, say SQR norm, and say, oh, okay, of vec is equal to vec.vec. But we don't need to. We can just say, no, we just want to use this once, and so we're just going to just put it in there. So GZB, I've never seen an implementation that takes medium density as a factor. So you're saying like the density of the air as the pendulum swings through it? And many does not even take pendulum density. So GZB, are you... Yeah, so previous question, and... are you saying, like, not assuming massless rods and kind of a... well, a distributed mass instead of point particles? Coffee. Because I think, like, as soon as you start to... If I interpreted right... okay, well, let's see. GZB. Yes, pendulums would not be affected by air, let's say, in space or in water. Right. Well, so... Wait, pendula would not be affected if they were in water? I off the top of my head, I would beg to differ. But then you start getting into fluid dynamics. Affected by air. Would not be affected by air. Oh, yes. Sorry. They would not be affected by air in water. That is correct. Yeah, they would be affected by the water. But yeah, if you were curious about, well, even just a simple pendulum in water, then I think you would definitely need to take into account the fluid dynamics, because like the different vortices for moving it around would affect, or would force the mass along in different ways with many different currents and things like that. But I am not at all experienced with like any sort of... Air is a fluid too, yeah. But I'm not at all experienced with any sort of fluid dynamics. But in the air, so it's also like just in projectile motion, 99 times out of 10, I guess if you're not doing a real world application, we approximate no air resistance, and it's usually pretty fine. Well, in the right conditions, no air is a valid approximation. But basically, what we're doing here is effectively in space. So, yeah, no fluids here. It's just cold solids. Yeah. Though not anymore, actually. I haven't done that research in maybe a year and a half or so. If the okay, so in space, the pendulum would behave the same if it was in the pendulum would behave the same if it was in a non-inertial reference frame. Or, in other words, accelerating at a rate of, well, you can change g to be whatever you want, but if it was accelerating. And that's the equivalence principle, and according to Einstein, you can't tell the difference. So, hey, Physics OH! Welcome. We're talking about whether or not the kind of standard implementation or representation of the physics of a pendulum would be the same in space. And hey, Tyrion, welcome on in, everybody. But yeah, so this implementation, since kind of the potential energy is only kind of dependent, the potential energy comes directly from being in a gravitational potential. And so these equations that we're seeing here are also perfectly valid, say, in empty space around, say, a black hole. If you're appropriately far away. Because yeah, or if you're in, these equations are also equally valid if you're in a rocket ship that is devoid of air and accelerating at 9.8 meters per second squared, or any other acceleration. Okay, so physics says, wish Melko reminded me to put on sunscreen. Yeah, it looked to be sunny every now and again over there, and the little bit that I did see. So you're lurking, but gotta do some stuff for your students. Yep, I get it. I mean, right now, you all are my students. Hopefully one day we'll have students. But yeah, so basically, the equivalence principle is a thing. Thanks, Doe. I appreciate that. Hopefully the faculty at the University of British Columbia will agree and see that. Single pendulum does not behave the same in space. What do you mean? Okay, so Ding Dong Man, is math for laymen yet? I know calculus is now. I'm not sure what you mean. GZB, yeah, if there was no gravity, or you were not experiencing any sort of acceleration, then then yes, the pendulum would not behave the same. In fact, you would, if it has any velocity, initial velocity, then it would just spin around. Yeah, emergency. I think in less gravity, or no gravity, rather. So ding dong. Calculus monkeys can do... What about other parts of math? Set theory is layman-ish. Are you saying that, like, are we now at a point that higher levels of math are more accessible to a wider audience? Yes? That's a good question, actually. I've never really thought about that. So GZB, that's what you've been talking about. We need edge cases in the pendulum algorithm. Well, I mean, in this algorithm, you can just set G equal to 0, and then you're good. Also, in this algorithm, you can set M2 equal to 0, and then you just have the same physics for the single pendulum. Okay, so let's see. Ding dong. Yeah, exactly. GZB, because I'm American. So logic was pretty easy when I did it. Yeah, I think... I guess restricting kind of the people that... Well, okay. For the general public, is math getting easier? I mean, off the top of my head, without, really putting much thought into it, I would say probably not. Yeah, so Picard, yeah, I would also say no. It's an interesting question, but I think definitely more of like a sociological one. I'd be interested to see the results of a study that came out on it. I don't know what that study would entail, but yeah. But say if we consider like students starting their say math bachelors, like are they going to have an easier time than their predecessors? Actually, you know what? I might change my answer. I would say at least maybe a little bit, because now with just how prolific computers and like different simulations of things are, like it's super easy to get an intuition for different things, like coding. Like if say you take an introductory programming class in high school, but you haven't really been taught linear algebra yet, and say, oh, I think this is cool, I'm gonna be I'll take some math classes. Or, well, probably if you go into computer science in college, you will take a linear algebra class. And then in that class, in the dedicated linear algebra course, you will see things that you have already gained an intuition for in applying programming methods. And so I think, yeah, just because of how... So I think in a sentence... because of how prolific the applications of specialized math has become to the general public, really without them knowing, I think, and if that trend continues, I think, quote unquote, math will get easier for people to understand. Introductory math, that is. So yeah, I think that's actually my answer. Okay, so let's see. Back up a little bit. I was surprised. So ding dong. I was surprised to see calculus. It is so well documented and so much easier to learn. Yep, calculus has been around for quite a while. So there's been a lot of work on it, and a lot of pedagogy has gone into teaching it. Or, well, let's see. Pedagogy. Pedography? I don't know. A lot of thinking has gone into exactly the best ways to teach calculus and like how people grasp with ideas and things like that. Math education as a study is very popular. Science education as a study is very popular. So let's see. So we'll document it. So GZB, are planets just pendulums with moving anchors? Yes. But also, the other masses on the pendulum can affect the above masses. Oh, but that's true on the double pendulum. The position and the velocity of, say, the second mass very much does affect that of the first mass. I'm gonna say yes, GZB, if you squint at it. So our pendulum, yeah. So Picard, people are too reliant on others, less likely to try. I mean, I could see it. Let's see. Okay, so ding dong. I think a good test for accessibility of maths is to see if engineers are being taught it. Interesting. Yeah, fair enough. Because, yeah, engineering will definitely just, engineering, you don't, like, learn category theory or quantum mechanics. And, if you're doing, like, chemical engineering, probably, but things like that. But yeah, in, like, other fields of engineering, you definitely learn about Fourier series and systems of differential equations and things like that. And again, with the rise in popularity of computers over the past, 20 years or whatever, computer modeling in engineering, I know, has taken off a lot. And so a lot of engineers use similar mathematical computing software like Mathematica, specifically MATLAB, I know is very popular in the engineering fields. And so yeah, I would say that would probably be a good place to start, looking at the math engineers are being taught. Okay, so Doe says, I think the visualization with computers has made it much more easier to learn math. I agree. I very, very much agree. And so that's actually one of the big things in why I've chosen and stuck with Mathematica for this long, is because of its visualization abilities. And it's like, I don't know how many times I think it's pretty much every time that, I come across some sort of, mathematical concept, and then try to throw it in Mathematica to try to visualize it and stuff like that. Because, some people can look in an equation like this one and just like, yep, that makes sense. And it's like, they can look at the different parts. Granted, I've been thinking about this, so I can look at the different parts and know, like, this is the kinetic energy of the second mass, and then this is the kinetic energy of the first mass, or not of the first mass, but some stuff. But anyways, well, I mean, that's exactly my point. But so you could plot or visualize, you could do some sort of visualization on this whole thing, and then also look at the individual kind of terms in the sum to get a better grasp on exactly what is going on in the physical system, and the relationships between the components that go into the sum. And I wouldn't be able to do that if I didn't have the visualizing capabilities of Mathematica. Okay, so I'm lagging behind in chat. So yeah, though I 100% agree. Visualization with computers has made it much more easier to learn math. Yeah. At least, you know, the things that can be computed. And even like pictures and graphical representations of, like, you know, using clever tricks and projections or something for higher mathematical concepts also apply there as well. Okay. Okay, so ding dong. I think we need to move further in visualizations of mathematics. The limiting factor to prevent the layman to understand mathematics is lacking the intuition. Where'd it go? Is lacking the intuition to see what is being shown to one. Yep. I agree. Granted, there are those that, you know, just have the ability to just visualize things in their head and it just comes naturally, which I think is one of the... In my head, that would be one of the driving factors on quote-unquote how intelligent someone is their ability to visualize things in their head. Because if you have some abstract concept and you can somehow visualize the relationships between different components in there, just in your head, then, I mean, you gain so much. I don't even want to say intuition, because it's like you see it and it just, like, that makes sense. There it is. And so that's actually a thing, like not everybody can do that. Not everybody can visualize in their head. And I am actually one of those people. It's a thing, it's called aphantasia. And it's actually mentioned in Space Force, the new-ish Netflix show. I just, like, myself and others just kind of, like, can't picture things in my head. So, like, the test is usually, so, like, picture a red apple. And, like, in your head, picture a red apple. And so then the questions are usually like, okay, well, what do you see? Some people say nothing. Some people say flashes or a very faint picture. Whereas others say, yeah, it's a 3D apple. I can grab it. I can move around and look at it in different viewpoints. And do all kinds of stuff. And I just can't do that. I get nothing. People say picture an apple, and I literally... a picture does not come into my head. So that's called aphantasia. It's super cool. Well, it's interesting. Aphantasia. And it's interesting, yeah. There's a cool video out there I might put in Discord later. Okay. Lacking intuition, yeah. So, ding dong, I think another problem is the extremism and gatekeeping of mathematics. Yeah. Elitism. I've noticed that most professors are super annoyed when a person has a hard time to understand concepts. Yeah. I mean, I was very lucky in my education to never have any faculty like that. where I went, everybody was very, very encouraging, and they were there to teach. It was an R2 school, so research came second, and everybody, all the faculty that were there, their primary goal was to teach. They wanted to teach and help people learn. And so I was very, I am appreciative of that. But I definitely know where you're coming from. And I think it also stems from like, it's really only a select group of people that are taught how to teach. People that go and get an education degree, for instance. And so I think that's a big problem with it. So like, you can know a lot about physics, but you can also not know a lot about how to teach physics. Very, very different. Though maybe Physics OH can maybe speak a little to that, since he is currently teaching students. Right, so emergency, we have ellipses, I think referring to the planets. I forget how that might fit into that context, or in the context of that discussion. Okay, so let's see, GZB. A while back I tried to make an implementation with an elastic string. Didn't work though. Right, so like swinging something around on a stretchy thing. Yeah, that would be interesting to like see some experimental data. So Doe agrees with me. And Doe says, yeah, you understand it if you can quote unquote program it. Right. Yeah, so that's actually that statement, you understand it if you can program it, is, I know, a big thing in math labs. It's like, you know, if you understand a concept and the algorithms that go into that, then it should be quote unquote easy to program it. And if you don't understand it on the most fundamental levels, if you don't understand the procedure and what's going on, then you can't program it. I mean, because programming is, you know, you're telling the computer what to do step by step. And so there's that, but I actually think this is where that's actually kind of what I like. One of the things I like about Mathematica is that the library of included and native functions is so large, and they've made it so easy to implement or to use those functions. And since it's all proprietary, it's such a black box. And so the thing about Mathematica, and one reason I've heard a lot of people say they don't like Mathematica, is that you do not need to understand it, but you can program it. You do not need to understand it to program it. And so So I think, yeah, that kind of thing about Mathematica, I think, is both a feature and a drawback at the same time, just depending on what your goal is to use it for. Because like what I do, and all my physics research was done in Mathematica, but like if I had to write all of my stuff procedurally, like in Python, it would just take forever, and there's so much code, and it would just be so much. And I don't need to understand how I really don't need to understand how some of these things are working. I just want a plot, or I just want to know the solution to this differential equation, or the integral, or things like that. Because like in that context, it's like if you're trying to model some physical system, then like you don't, the goal of modeling that physical system is not, well, can be, depending on actually, well, what your goal is, it's to gain an intuition and see how things move and model the physical world, and not try to understand the math and algorithms that go into modeling that system, or that describe it. So it's an interesting thing to think about. It's kind of like, not pedagogy of coding, but like more of just like meta science almost. But yeah. I will be right back in just a minute. Talk amongst yourselves. Okay. What are we talking about, fam? Okay, so let's see. Chat. Okay, so Doe says, with computers, Desmos for me, it's so nice to be able to change a variable and get instant feedback. Yeah. Yeah, that kind of keys into exactly the manipulation compatibilities, or capabilities of Mathematica that I also love very much. And so Emergency says, some people just can't think visually. I don't think that makes them less intelligent. I mean, I would agree. On the absolute, yes, 100% that does not make them less intelligent. I mean, well, no, I stand by that statement. I guess I would say the ability to visualize helps people seem more intelligent, if that's an appreciable difference. So Emergency says, I also can't imagine things clearly. Me too. Welcome to the club. Okay, so let's see. GZB says, can you try and implement elastic string into this algorithm? So this algorithm that I'm implementing right now, I think is one of the fundamental assumptions is that it's on rigid rods. I would have to think about it more. There was some discussion in the Discord about the kind of classic problem in Taylor, a spring hanging from the ceiling and a mass attached at the end of that spring, a massless spring that is. And so as it moves around, you get pendulum behavior, but also spring behavior radially. And so you can easily use Lagrangian mechanics to model that system. And so I think I would have to start from scratch in trying to kind of implement that same kind of behavior. But I'm sure it can be done. I'm sure it could be done. So GCP, is anybody interested in math here? I am. I got a degree in it. Also got a degree in physics. I double majored. And yeah, 2 degrees, 1 piece of paper. So Neuro, keep on kicking butt. Me? Just got back from cooking. Thanks, Neuro. I really do appreciate that. I try to put, I mean, I take this seriously, and I try to put some work into it and make it a good time for you guys. And I'm loving all this discussion, by the way. I really do. I mean, questions are welcome, as always. Yeah, no, I loved the discussion. I'm down to keep talking about it. And whatever questions you guys have. But it looks like I'm all caught up on chat. So if there aren't any more questions, I think it's time to move on in looking at the double pendulum. Okay. So no, Joe, that's okay. I'm very much down to talk about anything. I love the discussion. I really, really do. I know I said that, but I really do. Yeah, Nora, we're all about the tangents here. Yep. So GZB, physics is for mathematicians without imagination. I dig it. Why visualize in our heads when we can just look out the window? Or hold it in our hands. But granted, then you get into GR and quantum field theory. But yeah, anyways. So, I believe we got our velocities and the relationships between the tangent vectors, which is very important, which will come into play. And so now we just throw those velocities into our good old 1/2 mv squared kinetic energy formula. And so the kinetic energy for the K particle is 1/2 times the mass of that particle, and then the squared norm of that velocity. And so that's the kinetic energy formula. But you also see this thing right here, tensor expand. So why is this here? That is there because if it is not, well, okay. How do I want to go about this? That is there because of my inclusion of this kind of symbolic phi vector. Now, Mathematica can certainly handle vectors in their component forms. Well, exactly, in their component forms very easily. But the way Mathematica works is that if you represent a vector, let's say v1 and then say v2, Mathematica interprets this as a vector, and it interprets it as a vector, but rather these components are associated necessarily with an orthonormal basis. And so these tangent vectors are not orthonormal. They are not necessarily orthogonal to each other. And so we have to implement like this relation, and then basically this inclusion of tensor expand is exactly to tell Mathematica, hey, realize these vectors are tensors. These symbolic vectors are tensors, and so this is saying, do that, and then realize that this relation needs to get replaced by this. Sorry, my throat's getting really dry. Okay. Turns out talking for a few hours straight isn't exactly great for the throat. Okay, so Neuro, gonna head out, look for the notebook, and go through it on your computer. I wanted to make the notebook alongside you teaching. Cool, yeah, awesome. So have fun teaching, and hope everyone else has a lot of fun. Thanks, Neuro. Thanks for coming around. I think it was actually your idea for this, so thanks for the suggestion. I'm always down. I'm always open to hear suggestions to do on stream. And, yeah. Yeah, so bye, Neuro. Hope you come back next time. So GZB, what do I do now? What do you mean? Emergency, yeah. Must learn to have vocal cords of iron. Of steel. For those of you that were here on, I think, Thursday? This song that's on right now is from Hollow Knight. Okay, so GZB, what do I do for work? I enter data for the state of Washington. I am not currently in academia in any way. I would like to be. My plan is to, this coming application season, finally submit my applications to grad schools and try to get a PhD in physics. I would love to, I would love to computationally model quantum field theory in curved spacetime. Because that is exactly the intersection between my three greatest interests in physics. I love coding. Well, my two greatest interests of physics, and I love coding. yeah, it's pretty lackluster over here right now. So I just decided to kind of start this thing up, this whole stream idea, and teach what I can, because I have knowledge that other people would also like to have. Yeah, and the whole streaming EDU community, like the Knowledge Fellowship, TKF, which I actually don't have a command for yet, which I should have. They've all, been a huge inspiration to me. Physics OH as, the most inspiring. I've been a mod for his channel since he started, pretty much. And yeah, so this is my way to, I guess, still be a part of academics in some way. And yes, to keep the physics, math, and coding muscles sharp. So try to implement this in, I don't know what P5 is, but I assume JS is JavaScript. But anyway, whoever was, well, I didn't actually mention it here. I think I mentioned earlier, I was up really late last night, basically trying to fix an issue associated with Mathematica not knowing to basically automatically expand the dot products associated with these kinetic energy calculations. And so what I mean by that is, so let's comment out this tensor expand and do that. And so then we get things like this here. What is this? I trust you. I will look at that later. But yeah, so without telling Mathematica to expand these tensor calculations, this dot product, which is inherently a tensor calculation, then it will leave it like this. It will leave this dot product unevaluated. Okay, yeah, GCB, I'll take a look at that later. Yeah, so it will leave these uncalculated, and I, well, didn't want that. And so I tell it to, hey, expand those tensor calculations under the assumption, which we go all the way up here, hidden away, under the assumption that the phi-vecs are two-dimensional vectors. So that's some background stuff that you don't really need to know about. What's Mathematica? Good question. Yeah, so I actually ended up taking a long time to basically figure out exactly how and what I needed to do to make this work, and it came down to just putting this in here. Don't you love it when that happens? But anyways, now that we told Mathematica to expand our tensor calculations under the assumption that our tangent vectors are our phi-vec symbols are two-dimensional vectors, and expand our tensor calculations, then now we can just throw those into the total kinetic energy of the system, and we get this whole big deal. And we don't really need to look at it. We can go like that. But what we can do is come over here and make it a little neater to actually look at and understand. And so, what do we have? Oh, well, if we kind of look closely, this right here is exactly the kinetic energy of the first mass. And then, since we, in here, in this function, in the application of that function, we tell Mathematica to kind of group in the mass terms. And so, then we can see the kinetic energies associated on this, and then this whole term is the kinetic energy of the second mass. But, I mean, that's exactly how I have defined it. Yes, that is correct. Okay, so GZB Mathematica is... Sorry, I didn't know if you were serious or not. But I figured if you came to a Mathematica stream, then you might know what it is. But that's okay. So Mathematica is this program that we're looking at right now. And it's kind of the development interface for the Wolfram language. But I guess on a different note, Mathematica is a mathematical computing software. You could also call it a computer algebra system. Similar to the TI something 89, I forget what it is. But yeah, so it allows you to do things. It's kind of like MATLAB in a way, in the sense that it is a mathematical computing software. But it allows you to do many, many, many things. I hope that makes sense. One second. Okay. What time is it? 5? So, now we have our total kinetic energy of the system. So now, and with that, we have the two parts required to form our Lagrangian. So why don't we go ahead and do that? So if we come down here, and we go like that, and then we open our Lagrangian calculations. This one is much less documented. So, by our definition, getting into some live coding here, by our definition of the Lagrangian, just quick and dirty, L equals T minus U, we can exactly implement that, and so our Lagrangian is just the difference, and then we can say, okay, we want to look at it. And there it is. So this is the Lagrangian, the full-blown Lagrangian for the double pendulum. And it is beautiful. At least I think it is. I do think it is. And so I guess I've made a change to the TF command since then, but this is the same expression as the one down here. This thing right here. The full-blown Lagrangian for the double pendulum. And I do think it is quite beautiful. But it's pretty unwieldy. We have some cosines of our angles and squares of our velocities and more cosines and more cosines and a cosine, a product of these, and the cosine of the difference between the angles. And so if you recall from our studies of the single pendulum, the only way we can actually kind of get an analytic solution to the, well, without doing a bunch of math, the only way we can get an analytic solution for the single pendulum is to assume it only swings in small angles. And so that turns, oh, that scared me. Thanks, my man Ego. Thanks for following. I hope you're having fun and maybe learning something. And we do stuff like this. I try to do stuff like this. I'm still pretty new. Every week. Though probably nothing as kind of curated and well thought out. I spent pretty much all day yesterday on kind of really synthesizing everything that goes in here to try to make it a coherent and a good step-by-step kind of derivation of the physics of the double pendulum. But yeah, I hope you are enjoying what's going on here, and yeah, I hope you come back. We'd love to have you. But yeah, so much like, thanks Joe, I try. Yeah, so much like the single pendulum, we implement a small angle approximation. And so let's be good physicists and throw that in there. And so if you, oh, actually that's interesting. I wonder if it's because of that. Let's go down here and let's look. There we go. And so, oh, look at that. There's no actually. Oh, that's cool. Physics OH decided to give me money. What? Well, Physics OH, thank you for the subscription. You are the first one ever. I think it's kind of silly because I give you money each month and now you give me money each month. But yeah, thanks for the subscription. We'll be getting some, I'm really going to try to get some emotes going, some custom ones, and so those will be available, and yeah, we'll try to get some stuff going. It's all for the emotes, yeah, definitely. Look at that, now you even have the founder badge. But yeah, thank you so much. I really do appreciate it. Even if the monetary value by itself maybe isn't too much. Even though I really do appreciate that as well. What it means, what it represents to me is so much more. But yeah, so thanks for that. Thanks for the sub, and I hope the content stays good. And again, this is all because of you. Which is supposed to be a compliment. But yeah, emergency, if you both give each other money, don't you both lose money? Probably a little bit. Music, why did you stop? There we go. Friendship. For friendship! With the power of friendship, we can all lose money. Let's see. Okay, so yeah, what I was doing here, so up here, in creating the Lagrangian, originally, it had, Mathematica was doing some, actually, I may have, sorry, fast moving text. I think I took all the simplifications out. I think I did. Okay, but anyways, sorry, more fast moving text. So what I was thinking, you'll notice I include this trig identity transformation right here. And that's because in kind of approximating our Lagrangian, and that's because Mathematica was shifting the 1 minus cosine. It was transforming that into 2 times sine of x over 2 squared. But I needed to change that back to the 1 over cosine, so then I could apply the small angle approximation, where cosine is about 1 minus x squared over 2. But since I took all of these simplifications out, I don't need this anymore, because that transformation is not being made. But I'll just comment it out. Yeah, okay. But then so, kind of keeping it going. So yeah, let's be good physicists and approximate like none other. So if we take our Lagrangian, and then we make the small angle approximation, which is basically summarized by converting cosine to 1 minus cosine of x to 1 minus x squared over 2, and if both the angles phi 1 and phi 2 are small, then we're just going to say their difference is explicitly 0. And so the only reason this comes up is because of this term right here. And so the difference inside will go to 0, and then this whole term will just go to 1. Because if we don't do that, then it's I believe this whole thing is actually a transcendental function. So you can solve it numerically, which I tried to do, but didn't get very far. But anyways, another thing I will also point out in this instance is that in this application, I would, well, okay. It's an interesting point of why I decided, or why I needed to implement this exact expression. And that's because you could be saying, okay, well, non-dairy neutrino, why don't you just say phi 1 gets replaced with phi 2? Because then that would also take care of this expression right here, and then you'd be fine. But I don't, because if I did that, then every phi 1 term in this expression, like, well, not that one, I guess that is the time derivative of phi 1. So like this phi 1 and this phi 1 would be replaced with phi 2, and that's not what I want. I only want explicitly that the difference between them is 0. because what this is doing here, this is a repeated replace. This searches this expression, or rather this expression, and it says, so it searches all of that for explicitly this expression right here, phi1 of t minus phi2 of t, and it says, oh, and the only place that exact expression shows up is right here. And so I say, okay, change that to 0. And so this is an interesting case of not replacing single symbols, where usually that is what you should do, instead of trying to match larger expressions, which in this case, even just the simple difference is what I would consider a larger expression. But so anyways, between our small angle approximation and our variant of the small angle approximation for both of the angles, we kind of slat those substitutions into our Lagrangian, and then we have our approximated Lagrangian, or our Lagrangian approximation, shortened to lag-app. And so now, because we don't want to look at the code version, we want to look at the nice version, we can evaluate that cell, and then say, and now we can actually, I decided to represent our approximate Lagrangian, or our Lagrangian approximation, in two different ways. The first being as we have been, and kind of collecting terms to kind of highlight the different behaviors associated with the different masses. So that's this one right here. And so what we have is the approximate Lagrangian for the single particle. And so we can exactly see that if we just set m2 equal to 0, and then we just have a regular pendulum. So if we just get rid of that, then boom, here is our single particle, or our simple pendulum Lagrangian. And I think that's very illuminating. And of course, that is explicitly the kinetic, well, distribute the m, the kinetic energy minus the potential energy. And likewise for the second mass. And so I'd like this form because it's easy to look at and see exactly the different components associated to each mass. And it's just the energies are highlighted. And so I think that's a good way to, this kind of goes back to our conversation about visualizing things, but this is a good way to look at math and visualize the physical situation that's going on. Quote unquote visualize. To interpret, to get an intuition for it, just by looking at this expression. But, so this is kind of a good way to get physical intuition. But then this way down here, I've decided to kind of collect terms and represent our approximate Lagrangian as a polynomial of the positions, the angular positions, and its derivatives. So now we have the coefficient on the square of our angular position for mass 1, and and likewise going onward. And so now we have a quadratic equation. What am I saying? I think they're called homogeneous quadratic equations, or quadratic expressions. And so we have homogeneous quadratic expressions in phi1 and its derivative, and phi2 and its derivative. And so that is explicitly helpful for putting it into the Euler-Lagrange equations. so we can get our equations of motion. Tyrion, back from your walk. What did you miss? You missed a lot. We kind of derived the physics of the double pendulum from like starting points and took baby steps, and we also implemented it computationally, kind of letting Mathematica do the heavy lifting. So we, kind of sticking to the idea of not writing things by hand, but just starting from the basics and let the computer do the work. But so now we're here. Now we have our physical description and our mathematical description. And so now we can move on to putting our Lagrangians into the Euler-Lagrange kind of operator and seeing what happens. So yeah, I'll catch up when you start posting notebooks. Yep, I'm going to really try to, after this, I'm going to try to really hammer home on learning and setting up the GitHub. So all of the notebooks, past and future, are going to be up on there, and people can download them and tweak them and do whatever and just have them to play around with. Freely available and easily accessible science. What a world it would be. Okay. So, we have our Lagrangian. Let's put it in. So, Mathematica also, conveniently enough, has a native, pseudo quasi-native, what am I trying to say here? Ability to just implement the Euler-Lagrange equations via appropriately named Euler equations. And so here you can see I tried to give it the full Lagrangian, which you can do. We can evaluate it, and then boom. These are, well, let's see. Well, we're not going to do much with it, so let's say what am I saying? So let's collect and then put that in a column, and then so these are the Euler-Lagrange equations for the full, or these are the equations of motion, sorry, for the full-blown double pendulum Lagrangian. And yeah, we didn't have to do anything. We just put it in the code. Which this also comes back to what I was saying about you don't need to understand how the Euler-Lagrange equations work in order to use this function. You just get the result. You don't need to have an in-depth understanding of functional analysis to just get some equations of motion. But anyways, so yeah, there it is. And we didn't have to take any derivatives or do anything. We just put it in there. Let Mathematica do the work. But those are still pretty unwieldy. We still have sines and cosines and differences and things. Yeah, Tyrion. Sorry, we don't have a speak functionality yet, so you can't say it. I'll say it for you.
I say good day, sir.
There you go.
You get nothing.
Okay, but being the good physicists we are, let's use our approximate Lagrangian to get the equations of motion, and let's see what they look like. You feel better? Yeah. Okay, so what just happened? Well, so here we have our equations of motion for the approximate Lagrangian. But that's going to have to wait because we have our first channel point reward redemption. That's right, we do have a speak function. So if you have not explored the channel points yet, one of the awards is your choice to make me voice act something. And so there are two versions. You can tell me to kind of say a line, and then I choose the character that says that line, or for a little more, you can choose the character. And so emergency temporal shift has redeemed voice act for my choice. Okay, so emergency, what do you want me to say? I kind of already gave you one for free. Y'all one for free. But what do you want me to say? And then I can choose a character in which that says it. Oh, okay. Fair enough. Let's see. What would be... Okay, I got me. Okay, so this is... this is that one person in class that everybody hates and just loves to be pedantic. And remind the professor that there is this one thing that nobody really cares about and just is unimportant. And I will note that, emergency, that is not what I think of you. Get some things. Okay. Excuse me, Professor. We do have a speak function, just so you know. I mean, it's not really used a lot, but you know, I think in the context here, it would be better for everyone if we did include it. So, just so you know, we do have a speak function. How was that? That is almost physics, so yeah. It's like Valley Girl, but a Valley nerd, yeah. But yes, so you have the power to make me say things in different ways. What else do we have? You can also spend your points to be timed out, because that's an option. You can make chat emote only. We don't have any custom emotes right now, but you can do other things, or put only other emotes in. You can make me sing. You can make me sing a little bit of a song for as a reward. For enough points, you can add a command, though that one is subject to change. I still don't know how I feel about it. And then for pony points, you can invoke Twitch Plays Mathematica. And I don't have the functionality exactly set up yet, but that's going to be me running a program, so Twitch chat, so you guys physically take control of my keyboard and then try to write runnable Mathematica code. Or whatever you want. That's all I have so far. Okay. But Doe. Ooh, Doe. It was nice knowing ya. But can we still talk? I'm not sure what you mean, emergency. That's not what I wanted. Let's see. This is my first one. Okay, I see. I want to not do that. I want to say do. I'll see you next week. No, I'm just kidding. Alright, Do. Good luck trying to speak for the next minute. Alright, everybody. You are now fully free to say anything you would like about Do's here. Because he can't, or they can't say anything back. So, free reign. Okay, but can we still talk? Are you planning? Am I planning a sandbox? It just times out those. Yeah. What if dough got baked? Baked or banned? Oh, what if dough got baked? Then it wouldn't be dough, it'd be bread. And it's not bread is here, it's dough is here. Why does G have a value? Oh no, don't do that. There we go. Whew, you're back. Okay, welcome back, Doe. A sandbox, yeah. No, I would open a new notebook in a different context. Or it might be just funnier for you guys to screw me over. Okay, so anyways, continuing on. So here we are giving Mathematica our approximated Lagrangian and then say, hey, give us the equations of motion with respect to the first and second angles that vary with time. And we don't want to look at the code version, we want to look at the nice version. And so here we are. The equations of motion for the small angle approximated double pendulum Lagrangian. That's a mouthful. How you need to file permissions? Carefully. But yeah, so here they are. And so then also via Mathematica's very nice kind of desolve black box, we can say, hey, solve these, give it some initial conditions, and it will do so happily. And so the reason why, and so this kind of gets into the exact reason why we did approximate the Lagrangian, is because if we go back up here, our approximate Lagrangian here is, as I mentioned before, a polynomial, kind of a two variable polynomial in the angles and their derivatives. And so Mathematica can handle those types of differential equations rather easily. Or well, it's a polynomial and then you put it through the Euler-Lagrange kind of operator, and then you get nice differential equations, which are these. And so, yeah, approximating Lagrangian gives us a nice thing, which then makes the equations of motion a nice thing. And so we can actually I feel like these could be better. So there's one. And then, so now we have, so this is our independent term, and then here is our coupled term for the accelerations, angular accelerations. And then down here, we have a coupled term, and then we have an independent term. So yeah, now we have a coupled system of, or a coupled system of our equations of motion. But Mathematica is pretty smart, so we can just throw that in there, give it some initial conditions, which we can just stipulate via arbitrary symbols, variables, and say, hey, go to town. And then it does it just fine. So, let's see. Let's do that, and then go like that, and then have it do it again. And we say, give it to us. Show it all. And so, let's zoom out. Zoom, 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 zoom. So this is at 60% zoom, and this is the full version. This is, oh wow, this is very long. This is the full version of the analytic version of the solutions to those equations of motions. Okay, that's just flashing. I don't want to give anybody problems. But yeah, so it has all that under the hood. And going right there. Sorry, getting the right zoom for you guys. Anyways. Text, text, text. But we don't actually want to look at all of it, so we can just delete that. And then if we really want to have the skeleton, the short version of it, we can just make it run it again, because it was pretty easy for it. But so yeah, that big whole monster is encompassed kind of in this formatted, displayed representation here. And Mathematica is very nice because it just kind of shortens all of the very long bits in these little kind of cells here. But we don't live in a world of arbitrary variables. We live in a world where gravity is negative 9.8 and lengths are not abstract, but they are real numbers. And so we will say, hey Mathematica, tell us the equation, or give us the equations that model the angular values for this system given a double pendulum where each rod is of equal length, 1, and each mass is of equal length, also 1. I'm going to commit heresy and say units are not important here. You could also non-dimensionalize this, which I did not or have not yet, by saying the ratio of these different lengths is some unitless factor, and then that would actually be more appropriate to compute. But anyways, so we say, hey Mathematica, gravity's this, our parameters are this, do the thing. And so here we go. Here are our solutions. Here are how our angles evolve in time. Well, for arbitrary initial conditions, that is. But what if we don't want arbitrary initial conditions? What if we want initial conditions being what I tried to do up here? And we say, okay, what if what am I doing? What if What if we don't want arbitrary initial conditions? What if we want to actually say, hey, the first pendulum, or the first mass, it starts at an angle of pi over 4, and then it also starts with a 0 velocity, so it starts from rest, and then the second pendulum starts at negative pi over 4, also with 0 velocity. And we say, okay, tell us what it is, and we'll see if it works. Right. But we're not interested in the symbolic version anymore. So let's get rid of it. And there we go. There we go, fam. So emergency, can you plot this? Yes. We can plot the angles by themselves. We can say, well, what we can do is say we want the previous output, but only the first part, and then within that first part, only the second part. Blue line is, well, we can actually just say, hey, or not plot labels, plot legends, and we can say phi1, or yeah, phi1 of t and phi2 of t. And so, see, this is interesting. And this actually behavior was something I did notice earlier that had me kind of worried, but yeah. But so what I think the problem actually is this negative sign. So let's go back. Now let's try it again. Hey, look at that, chat. Now I'm not exactly sure how it is actually plotting this, because these imaginary parts Because as far as I can tell... Wait. Never question the magic. Pretty much, yeah. We still have eyes. So what we can do, via the magic of complex expand, we can say... Yeah, that's what it defaults to. I mean, so these expressions are necessarily evaluating to real numbers upon a given t, but I just don't see how. I just don't see how that's possible. Okay, time to put TNG on in the background. That's always a good choice, Tyrion. Yeah, Tyrion, you know it's a coding stream, but by the keyboard clicking sound. Yep, that I'd say that checks out. But if we just ignore the magic for a second of what's going on, or of how this expression turns out to be a real number, then there we go. These are the plots of the angles as they evolve in time. Coding, TNG. Okay, so emergency. Did plotting fix things or break things? Plotting did neither. Plotting illuminated a problem. And that problem was that my inclusion of a negative sign on the gravity was incorrect. And I was thinking about it when I did that in the first place, whether or not I should include it, and I ended up including it because the expressions that immediately came out were manifestly real, whereas these expressions include imaginary numbers. They include complex numbers. But I think it's, well, okay, let's see. Plotting fix things, Tyrion, all complex analysis resolves to real numbers. That statement makes me uncomfortable. At worst, with zero real part, right? Yeah, so they all have zero real parts, and they all have zero real parts. They all have zero real parts. I mean, what we can do is also say, hey, give us numbers. Oh, it made E interesting. I mean, so these are oscillatory functions. I mean, but oscillatory is what we want, but it's manifestly complex. Okay, emergency says, just do the absolute value, sweep them imaginaries under the rug, right? But it's just interesting, because if you give plot an imaginary number or a function that outputs imaginary numbers, it just won't plot it. It won't automatically like take the modulus or anything like that. It just won't plot it. Which is why I know these expressions are evaluating to real numbers, because it is plotting it. Plot only gives something. Plot gives something if and only if that something is a real number. So, but I'm just failing to see how these expressions come out to be real. We can say, so let's take out that. What if we do complex expand outside of the simplify? Look at that, chat. Real. Wait, no, I lied. There's an imaginary. There's an imaginary. Okay, what if we don't plot it, and then we say, interesting. Oh. Okay. So it looks like plot. Okay, so the imaginary components of the evaluated numbers are very, very, very small, on the order of 10 to the negative 16. And so probably what plot is doing is that in the definition of how plot works, it probably has a chop function, which takes numbers that are close to 0 and makes them 0. And so, what's probably happening is we go over there, and then we go like that. So it's just that the imaginary components are, well, more or less actually 0. The chop function, yeah. Yeah, Tyrion, I feel that one. Okay, so what if we got rid of that and we just say there's some stuff, and then, I mean, chop only works on real numbers. I mean, it's just interesting. But anyways, so yeah, I believe that is what's happening. So yeah, chop. Emergency says, is it solving the equations in the wrong domain? Should they be part imaginary? Is it solving the equations in the wrong domain? So, well, so it's also something I was thinking, because these are the solutions for the angles of the pendula. But how that angle changes over time should be oscillatory. Well, which is exactly what we have here. And so, yeah, since we want that oscillatory motion. I mean, but for the angle itself, I was thinking that, you know, having that imaginary component for the angle makes sense. Yeah. But it's something I think maybe I just need to think about more. Ooh, look at that. Pretty. Oh, it looks like we have some interesting artifacts. Let's go out to pi. That's a good illuminating. So now usually what I like to do at this part of my investigations is, well, play around with the values. So like, what if we make the second length, the length of the second rod, twice as long as the first one, while keeping the masses the same? Look at that. Whee! What if we make it 10 times as much? How long would it take to display the double pendulum itself? Ooh, look at that. We have some, I think, underdamped behavior. So that's something we can do. Definitely. Emergency. And that's kind of what I wanted to do, but just didn't get to it before stream. But yeah, no, that's definitely something we can do. And we shall, because that's something I really want to see. And then maybe we can actually make that GIF. This is cool. This is really interesting. But it's linearly, on average, increasing. Whee. Cool. But yeah, so let's highlight that, and we say divide cell. And so then we come up here. Here's our approximated Lagrangian. Here's our things. Here's our initial conditions. So let's say with incons, or init. Let's say init. Well, init cons, and then we yeah, let's just delete that. And we go over there, and we go like that, and we go like that, and we go like that, and we come down here, and we go like that. And since this is relatively short now, we don't need to line break it. Okay, so how long is it? Emergency, remember that one to show later. Yeah. Okay, so let's see what happens if we do that. Well, we could. What is happening? Oh. Okay. Anyways, we do not want to look at these anymore. Oh, but what we do want, so that's initial conditions, and then we're going to change this to a block. Right, I already tried that. Okay, we're also going to... You can tell this is the part I haven't prepped. Okay, so what we're going to do is stop recalculating the Euler equations every time. And we're going to divide cell. And we're going to calculate them. And say... Jeez, loud car. We're going to say clear EQ of motion. EQs of motion. Or actually, you know what? EOM. There we go. And we go like that, and then we say cool, and we say that is a C. And we go like that. And then we say EOM, and then we go like that. And it doesn't do anything. Because we need to rejoin these two, and then this gives us the equations, or the solutions, and this will plot the solutions themselves, but, well, yeah, let's go like that. And then down here, we can say, yeah, there's that, and then down here, we can say, yeah. And then we get out our good old graphics. And we say, let's make a line. And we call that line a thick line. And we go, that line goes from, oh, I don't know, -2, 0 to 2, 0. And this will be our ceiling. So we'll close that, and then we come down here, and then we will make our rods. And we say these are also thick. Then we don't need a space right there. And then these lines are going to be from right, because line takes multiple arguments, and so we're going to say well, this also needs to be in a manipulate, and we say our line goes from 0, 0 to, okay, there we go. I got my bearings now. And then to the point, it's going to go to the first point, and then another line from point 1 to point 2, and then we're going to close that, and then we're going to say, now we make the points themselves. And then we say, okay, these are all going to, wait, no, points aren't there. Points have point size of 0.00 or 0.03, and then they're going to be red points. And then the points, oops, go from point 1, or there are points at point 1 and point 2. And then that's all the points we want. And we're going to say plot range goes from... well, we're going to say all, because that should include the ceiling line. And so, after all that, we can say... we can put this whole thing in a block, and we can say 0.1. We can say 0.1, say of t is equal to what am I doing? Well, if it's because if that's there, then we need to go. So that's the angle from the vertical, and then. Sorry, I'm talking much less because I actually have to think now. We have to think about the actual positions of the masses in space relative to the origin, instead of, say, their starting positions. Well, do we? This is riveting content, isn't it? Well, if they're rigid rods, then the point is going to be on a circle. It's going to ride on rails. So it's going to be... Let's see. Yeah. Yep. I could do that. Okay, well, okay, we're gonna practice bad coding, and we're going to say len 1, but we're not gonna do that because currently length 1 is just 1. And so what we're going to do is go cosine of, go away bug, phi of 1 of t, and then sine of phi of 1 of t. That's what it was. And then this is the values. So we're going to change dsolve to dsolve value, so it gives us the expressions themselves instead of a list of replacements. So we'll do that, and then alright, but anyways, and then 0.2 of t is going to similarly so this is this vector right here is a position on the circle of length this coefficient up front, and in this case, length 1 is just 1. And so I'm not actually going to put anything there. And then this point is the position on a, well, this vector is the position of a point on a circle with radius length 1, which is currently 1. And that circle is centered at the origin. And then, but for our second point, the center of our circle upon which the second mass moves is not the origin, but rather the first point. And so the position is relative to that, point 1. Well, it could be cheeky and say it doesn't like that kind of syntax, but it does it. Okay, so then, okay, so there's our graphics, and then we come out in our manipulate, and then we go t from 0 to, oh, I don't know, pi. And then, oh, but it's also an animator, because we want it to play on its own. And up here, we say, why does it not like, oh, that's right, because I was confusing things. So it doesn't like that. Why doesn't it like that? Manipulate. Oh, what? I didn't do what I wanted to. Hello? Oh. Am I missing something? Oh, there. No, that's not. No. There we go. That's weird. Why does it not like that? What if we just said, I don't care what you think, and just did it anyways? Oh, that's not going to do anything. Abort. Oh, that's interesting. Yep, it doesn't like that. That's because block local specification contains, which is an assignment 2.1t, only assignments to simple sort of like, yeah. Yeah. So in this case, you have to be rather pedantic and say pt1 is a function of t, and then this, no, that's not what I wanted. And then pt2 is also a function of t. Oh, it didn't not run. It just didn't show us anything. 0.1 should be a pair of numbers. Here's 0.1. This is a weird song. Okay. So this should be a point. That should be a point. Da, 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 da. That's a point. This is a line. This is a line. Okay, so it's not evaluating PT1 and PT2. Why? Why does it not like this? This is when we comment all that out and do some debugging. PT1 of T. Oops. Let me say PT2 of T. Okay, so it gives us points. Oh. That is because I have not told it what the fees are. Or at least that is a problem. Anyone still there? Very riveting content. It's really just watching me think. Okay, so let's see. These are our values, and then we say, okay, well, let's come down here. You're jazzing out, yeah. This is some groovy. So there's one, there's two. Oh. Okay, well now well, yeah, I don't want that. What was this? One, all, two. And then, and then save, and then see what happens. But first, let's evaluate. Force evaluation. Okay, still doesn't like it. I really don't understand why. I don't think I've ever seen this kind of behavior before. I mean, I think manipulate is module under the hood. And so, I mean, I think it's just a, well, here we go. Good job, chat. Oh, not good job. Right. Well, but it would need to. This is not the best way to do this, but I just want to see the picture. So, oh man. Oh, because, yeah. Debugging, so much fun. Coordinate data should be a pair of numbers and scale of operators. So, does line not? No, it does support a collection of lines. Let's see. Emergency, can you parametric plot the X and Y? Yes. You'd have to convert it, though. I mean, it's just a polar to Cartesian. But yeah, you could. Oh, yeah, and that, I just did the conversion right here. It's just x equals cosine. Would that be easier to do? Probably not. Well, I mean, that is exactly what I am doing. As far as I can tell. I've been staring at this for a few hours now, so maybe my brain's all mixed up. Okay, yeah, it doesn't... I can't do that with width. Well, in that case... Hey! Hey chat, guess what? Oh, that doesn't look right. Oh, it's moving a little bit. Hey chat, guess what? Okay, everything is one. Oh. Let's go like that. So those are one, that's gonna be maximally 2. Gravity is wrong. That's interesting. Yeah, that doesn't look right. Wait. Oh, no, it's just rotated. It's just rotated. It's just rotated. What am I doing? This is not the best way to do it. Well. Oops. Yeah. So let's just rotate it. And then also rotate this. Whole thing. Okay, delete all, save, run again. Hey chat, guess what we made? Y'all are seeing this, right? Can I get some hurrahs in the chat, please? I'll put it in there. Actually, don't want 2. We want -2 to 2, and then what happened? Oh. It's beautiful. And, well, let's see. I'm not going to mess with it too much right now, so we're going to do things the hard way. But yeah, so now can you make a little trail? Jeez, I go through all that and you still want more? Come on. I'm just kidding. Yeah, we probably can. But just look at it. It's a little bouncy boy. Okay, I want to change some parameters. Okay. Here, I want to start a poll on what parameters we should change. Because this is an interactive stream, darn it. We can change gravity. We can change lengths, or we can change masses. Or freeform. And just change all of them. Okay, chat. You cannot see the poll. Where is the poll? I see that it sees the poll. I cannot see the poll. I have no idea where the poll is. I have no idea where it is. That's weird. I'll have to look at that later. Oh, that's interesting. And questions? What kind of questions? Oh, not a good test taker? I mean, is anybody really a good test taker? Actually, I can think of a few people. Pick C on the poll. Masses? Let's see. Let's see. We'd also change initial conditions. There's a lot of things we can change. Let's try that. Just for starters. Well, that's not very illuminating. Put it straight up. Oh, that's a good one. Let's do that. Okay, so let's go... Nope, that's one. Such bad coding. Okay, so let's see. I would also like to... Well, I guess it's a change. Well, but that's going to change. So putting it straight up, we can certainly do. Whether or not that is a valid set of initial conditions under the small angle approximation is another story. Okay, let's say the first one starts straight up, which would be pi. And then the other one also starts straight up. Well, it is an unstable equilibrium, but it is an equilibrium. But so let's see if our code catches that. Oh, look at that. That's interesting. In my head, it should be... like nothing should happen. Okay, I'm over this song. Oh, that's what I was doing. Whee! See? Because it stands straight up, but then... Yeah, that's just interesting. Whee! Wow. Whee! Okay, any other suggestions for parameters? From anybody? What? It's bouncing up. What do you mean it's bouncing up? Oh, like right there? And then it goes up. What about the length? Yeah, we can change the length, though. Okay, so yeah, now I'm curious about that. Okay, so it's going up. And then... Let's slow this down. Okay, it's going up, it's slowing down, and then it's coming back. Right, so... Alright, hold on everybody. Chat amongst yourself for just a minute. I'm getting a phone call. Okay, we're here. Whee! So goes up, that one slows down. Interesting. Yeah, it's kind of like there's a spring attached to the top one. Interesting. I don't know. I mean, it doesn't seem impossible. Actually, that's interesting that it just wouldn't like loop back around, and it actually stops and comes back the other way. You know, I'm curious, chat. What if we put in a negative sign for gravity? That checks out. Yeah, the angle's just... it just doesn't work. Oh, well, that looks right. Wee. But then it like picks up speed. Yeah, the rate. I mean, there's no conservation of energy in this one. I mean, it looks like there's like a divergence at pi, though. And like these are the angles, but the rate of the angle, just like that's not how that works. Does zero gravity work? Let's find out. Beautiful. My goodness, chat. We have done it. We have unlocked the secrets of the universe. It's just so gorgeous. Physics works, everybody. Physics works. Can he give it a push? Yeah. God, this is such bad code. Okay, parameters, initial conditions. Let's give the first one a little push. Oh, doesn't like that. That's interesting. That's very interesting. Why would that be? I mean, it's simulating a free particle. Is it just because... Yeah, well, I'm thinking with no gravity, it's a free particle. And so, well, and if we give it a push, well, does that work with gravity? Yeah? Yeah, that checks out. Granted, it was already exhibiting odd behavior from the straight up. Well, we may get a bigger push. Give it a super small gravity. That's not right. That's not how gravity works. Also, why is it going left? I told it to go right. Wait, did I tell it to go right? Is this flipped? Is this upside down? There we go. More time. Okay, calm down. Yeah. Wait, that doesn't make any sense. Okay, that's... Yeah, it's gaining energy. Look at the equation from Taylor's classical mechanics. Well, I mean, maybe one of the problems... Well, okay, so let's do a sanity check. And if they all start from 0, and... Well, let's do positive. So this, nothing should happen. It should be stationary. Yep, look at that. Now let's say the what am I saying? Now let's give the first one a little nudge. Yeah, no, that checks out. I mean, again, as I pointed out before, our implementation is only valid for small angles. So, what we were seeing actually should make sense. Those angles were not small. Well, small angles of deviation. Well, no. Because the angles are measured with respect to the downward pointing vertical. The angles we were giving it was pi. Get a better formula, Scrub? I mean, with small angles, it looks to be good. And as far as I can tell, all my formulas agree with Taylor, so... Well, Taylor actually does some other stuff. See, that looks right. Also, what's the equation at the bottom? What equation? Oh, at the bottom of the screen. That is the full-blown Lagrangian. Without any approximations. Look how nice that is. Whee! Let's see. I'm going to clean this up off stream and make it like a much nicer environment to play around with also. What if the second length was twice as long as the first one? It doesn't look twice as long. That doesn't look chaotic. Eh. I mean, it's just sensitive to initial conditions, is what chaotic means. And so I will also work on... Let's finish that poll. Like, it should still look smooth. Whee! Let's give it a little more. Yeah, I mean, chaotic functions can be periodic. It's just there's this thing called period doubling, which is very interesting. I'd say look at the logistic map for a good example of that. Look at that. Whee! Let's give the bottom one a little bit. Also, can you teach with a student edition? What do you mean? Like an actual course? I should put the initial conditions. Can you teach with a student edition of Mathematica? Like, what do you mean by teach? In what context? I mean, this is just me playing around at this point. Oh, that's because... Also, I kept thinking, like, why is this diagram, why are the lengths of these bars not changing? Like, are you supposed to have some special educational license? Well, I mean, if you're teaching, if you are using Mathematica in an academic course at, like, a college, then, and, like, you are a faculty member, maybe you might need an educational license. Well, I mean, they have deals for universities, but I think the individual licenses may be just regular licenses. I'm not sure. That's weird. Maybe it was too big of an angle. Bum, bum, ba-dum, ba-dum, bum. That doesn't seem right. Well, okay, well, again, I mean, that's with weird lengths that we're not actually seeing because I didn't want to do that. How about we make the first mass twice as massive? That checks out. So what if we make the first mass twice as massive, but then it has a small initial velocity, and then we start the second one with, oh, I didn't even see that. Let's just start these from rest. Oh wait, no. That's at rest. That's at rest. You're gonna start at, let's say, pi over 6. And then you're gonna start at negative pi over 6. Go figure. With the symmetry, you just kind of get it back and forth. This is a good song. Let's also change that back there. And then we're going to say, we're going to have the first one start at pi over 4. Let's go so fast. Oh, that's because it's going for a long time. That's not 2 pi. That's 1 pi. There we go. I like that one. Very bouncy. Well, chat, I think this has been fun. Hopefully y'all learned something. Emergency, hopefully I didn't scare you off with my shoddy programming. Yeah, thanks for sticking around, Doe, and whoever else is out there. I hope you had fun, and maybe even learned something. And I think we will maybe revisit this. I might just add a few more things off stream. But I think this is a good place to stop. I'm very happy with this animation right here. And if it helps you never learn anything, well, that pretty much sums up what I learned, my experience in statistical mechanics. But I hope you all have a great rest of your Sunday and a happy Labor Day for those in the US. And I will, again, try to get the GitHub set up and make this notebook and the ones we've done in the past available to y'all. And yeah, I hope you all had a good time. Learned something, saw some cool code. Yeah, I really like this. I like streaming. And hope you all like me streaming. I guess if you're here, then you do. But anyways, I bid you all a good night. And just hope you don't have too much fun, you know? Just have the right amount of fun. But with that being said, is there anyone out there to raid? Try. Twitch. Oh, that's okay. There we go. Oh look, Physics of Witch is hosting me. Also, if anybody noticed, the quality of the stream should be a little bit better this time. This time around, I upped the bitrate and the FPS. We're now streaming at 720 at 40 FPS with, I forget what the bitrate is, but yeah, so it should seem a little smoother. And I may up it more as well, because we did pretty well in terms of frames missed due to rendering lag. So yeah, we may step it up. But anyways, so let's see. I can see that Laboratory 424 is on, Lantern Noir is on. Anybody out there have any suggestions? Want to guide the raid? Because if not, I think we may go to or Yodel. Anyone? Okay. Let's read Lantern. I've raided Taiwan's the past few times. That's been late at night, though. Okay. Lantern Noir. What? Lantern. Is it two N's? Yes, it is. Okie doke. Thanks for chatting and really being a great part of the community emergency. I do appreciate it. And hope you all tune in next time. All right. Bye now.